So we are indeed live, and it looks like it says sending data. Double checking, double checking. Gummit. All right. I'm going to make an assumption, and the assumption is that we're live. So it is Thursday, and we got Mr. Hussey with us. Matt Hussey, thanks for joining us again.
How's
Good
it
to,
going, Tom?
it's going pretty
I
good.
almost debated putting a tie and suit on.
No,
Feel
no,
like I
this
need
is
to up the game.
yeah, you gotta up the game, brother. Gotta love it. It's all
Yep.
good stuff. So we're gonna talk arc resistant. I did have, and I'll have to check my email again. I had one question come in on over email, which is not really related, but somewhat related to the discussion. So I'm gonna try to do what I can to answer that one. Let me just double check my volume. Why don't we just do a volume check since we didn't get a chance to do that? But
You good, Tom? Can you hear me?
yep, we're
Audio
good.
coming in good? All right.
Coming in good. So Matt, why don't you do this? While I adjust some things here, and people start filing into the room. Why don't you just give us a little give us some of your background. Tell us who Matt Hussey is.
Uh-oh. Well, I grew up in Pittsburgh, so I started
Oh,
my career with Eaton actually in Resi. So, Tom, at
okay.
one point I think we crossed paths a little bit. I worked with residential products as well as like molded case circuit breakers. From there, I ended up getting really into manufacturing. So whether it be motor control centers or medium voltage switchgear was actually when I first really got my first taste of arc resistant testing. Was right when I was working with medium voltage switchgear. After that, I spent some time at one of our satellite plants, which you probably are familiar with. Spent some time in the greater Chicago area,
Ah,
and
cool.
then the past 5 years, I've been focused on the MCC product line. Once as kind of a field AE or field application engineer for the product line, and then currently a product manager for MCC. So
Ah, cool. Product manager. So you're
yeah,
the BMOC, right? Big man on campus.
somewhat like that.
Absolutely. So cool. So our discussion today is about arc resistant equipment, and I think a lot of people have the misconception that arc resistant means you can't have an arc inside of the
Right.
equipment, and that's farthest from the truth, isn't it?
Yeah. Yeah, it really is. And Tom, I think some of that is, I think over the years, this equipment has really become more accessible, and I think more industries are considering this type of equipment. So I think, maybe there is a bit of a misnomer that exists out there, um, understanding how this equipment is tested and what it's intended to do. Um, as we were talking about this earlier, I think one of the first areas in which arc resistant was really explored was in medium voltage applications. If you can imagine, there's a tremendous amount of potential up there. So having the equipment perform on an internal arcing fault, which, as we'll probably get into, is a lot different than what you would experience under a bolted fault condition. And there's an entirely different set of phenomenon the equipment goes through. And in reality, this is equipment that is designed to contain those effects, and as well as try to minimize that exposure from that equipment. So,
Yeah, and that's a do you want to? I know you sent over a couple videos. You want to? Do you think it would be good to show maybe something that doesn't pass and then what does pass to help people
yeah,
understand that difference?
I think it would, and we'll probably use that as kind of a backdrop, and then we'll get into really what goes into it. I think the one I sent you with like a no pass is actually probably one of our medium voltage switchgear lineups from a number of years ago. And this was, this is equipment that's taken to a test lab. Uh, a certain prescribed fault level is associated to the equipment, and we'll get into some of the testing details. Um,
Okay.
but But basically, this equipment, you'll see a video, you might hear some sounds on it, but
Yeah,
let it
they're
run.
so they'll hear it, you won't.
Gotcha.
Just so you know. Okay, I'm
Yep.
gonna try to just put the volume a little bit because I'm not sure. All right, here we go. This is a no pass. So this is a piece of equipment that has an arc flash event inside of it, and it does not pass the arc resistant testing.
Yeah, that is a ungood scenario, right?
Yeah, it's interesting. You can hear the alarms from the nearby cars.
Well, no, there's actually an alarm in the Tesla. They
Oh, okay.
they depress it right before they initiate as one last final clear out.
Oh, I gotcha. All right, so I'm just looking. So look. If I just look, I'm just going to like take a look at some
Yeah.
of the frames,
Hmm.
and you can see where the arc ignited. Looks like they did the ignition at the bottom of this equipment.
Right. This might have been medium voltage switch gear. That might have been a breaker compartment, and we'll get into how they test various compartments. But yeah, that might have been where the primary location is, and in reality, you'll see an overhead plenum, but you could see there's a tremendous amount of energy that's released from this equipment, which is not the intent of the design here. Is really to contain that
They,
hazardous energy.
I think they call that an unintended rapid disassembly in the field, or something like that.
Yeah. Right.
Okay, so now the next video is a pass.
Yep. So pretty stark difference there. I mean, you still see quite a bit of you know escaping of energy toward the top of the equipment there, but as you can see, the area under examination is actually that whole test stand, and we'll get into that a little bit. But that's basically allowing and protecting. If somebody was standing in front of there, uh, they're not experiencing. You can see how very clean that entire front of the equipment is from if anybody was in front of that at the same time.
Yeah, now that's all vented out the top because the energy has to go somewhere, right? I mean,
Correct.
you,
Yeah. Yeah, and it's one of the challenging parts, when you get into such high voltage and duration, whether it's low voltage switchgear or medium voltage switchgear, there's so much energy that's built up. More commonly, what you'll find in arc resistant switchgear is a lot of need to vent and deal with the rapid pressure buildup in the equipment. Um, it is something that has to be considered in the design, but as you can see, the rest of the equipment has been you've got a balancing act, right? You've got to make the structure strong enough to hold it back, but that obviously redirects that energy somewhere, so it has to be dealt with.
right. And that's and that's an interesting perspective that like you said, you have to be able to control when we say arc resistant equipment. What we're talking about is that we're just basically the arc occurs inside and we contain it and then maybe put it to a
Yep.
different area so
Yep.
we take it up and out, so to speak.
Yep. Yeah, and there's various classifications we can get into, but basically, this is an entirely different phenomenon than what you might see from our normal UL short circuit testing, right? Any of our withstand or short circuit current ratings, as you know, are established based off of a voltage fault condition where
Right.
essentially the voltage very quickly goes to zero. So the electrical system is holding itself together. An arcing fault, you have a much higher impedance present. So there's a tremendous amount of expansion of gases, molten copper, you know, that type of energy releases a lot of energy into the surrounding area.
Yeah, and like you say, I think a lot of the safety aspect of electrical equipment, they start in that equipment that has the biggest hazard or that has the most likelihood, right?
Yeah.
And then what they try to do is what'll happen is it'll migrate its way. Like if you think about like the electronic trip units, right?
Yep.
Back in the day, we didn't have electronic trippings. Then we had an electronics, and then
Yep.
we did ground fault protection of equipment, and
Yep.
we did that in like larger types of relays that shunt tripped something, and then we put them
Yep.
into the breakers, but it was the big breakers, right? And now we've
Yep.
got residential breakers that have these brains, and so it just migrates its way into other areas as we find those value propositions.
For
So,
sure.
all right, so those are the two videos that you had. Um, so you want yeah, how do we want to start the discussion out? We got Tamaki on Tamaki. We got your I got your question. We're going to answer that one here as we start going through this. We got Felix Sandoval in the house. We got Robert from Omaha. Just looking to see who we got online. We got the Michael King,
All
the
right.
Michael King, man, David Rodriguez. So this ought to be good. And so if you think about this, Matt, on Tuesday we had Scott Margolin, who I inducted into
I
the Buck
saw that.
41 Club. That was a
I
really
saw
good.
that. I tell you what, it was great, to see that side of what goes into it from a PPE. I listened in on that one. It was, it's amazing, right? We're designing all this wearable clothing and everything to
Yep.
withstand these effects, and it was really interesting. Even the topic of layering, right?
Oh
As you
yeah.
were talking about, um, making sure that you have the right clothing underneath as well as what your main defense is, right? That was really good discussion there.
Yeah, I enjoyed that, and he's a very energetic guy. So we went from personal protective equipment. Now we're talking arc
Hmm.
resistant equipment. And then next week on Tuesday, we're going to have Russ Seyfried, and we're going to be talking about getting outside of that arc flash boundary. But now this equipment is designed to contain the arc flash. So I mean, when you watch those two videos, I
Yep.
think you get the understanding that when you have the doors
Yep.
open, it's no
Yep.
longer arc resistant, right?
Yeah, absolutely. I mean, you could see it very clearly in those videos. We're certainly depending on those compartments to be latch secured, and I think you've even seen some of that language authored in NFPA 70E. Um, but yeah, it's entirely built upon that. Now, granted, there is some compartmentalization where you might have. Well, that was a good picture you got there. Where such a compartmentalization, you might have these various circuit breaker compartments, but you might have a control compartment, such as what's indicated at the top there. There's some compartmentalization where whether you're accessing those pilot devices or those switches or other relay cabinet areas, you could be protected in those compartments should an event occur in an adjacent compartment.
Yeah, and you know what? A good pic. Here's a good photo of that. If I can get this one
Yeah.
to pop up here, there it is.
Yeah,
So
and it's pretty good discussion. Even on the labeling of this equipment, you're going to see some signage to note as well.
yeah, so this says now there's the type 2B, and we're going to talk about what 2B
Hmm.
means, and I'm learning on this as well. So that's this is the interesting thing is I mean, arc resistant equipment is not like it just came out. I mean, you and I were
Right.
talking about this the other day, and I went back to IEEE, and I found that it's around 1994 that you start
Mm.
seeing IEEE papers at Petrochem, the PCIC, and then Electrical Safety Workshop. And it was back in the mid 90s that we started talking about arc resistance. So, someone, to your point earlier, you made this statement, and it's very valid. When we always historically looked at equipment through the eyes of um, short circuit current ratings, these high
Yep.
fault currents, right? And
Yep.
I think someone over here um, made the statement, and I know I saw it. We talked about the magnetic mechanical forces,
Yep.
right? Now, when you think about those, oh, we're going to get the type difference between 2B and 2C. You hang in there. Oh yeah, it's good
We got the
questions.
live audience.
Oh yeah, this is good. So when you think about what we used to do, and we still do, right? We worry about that three-phase bolted fault, and the bracing being able to hold together under the magnetic forces, but
Yep.
arcing currents, which 2002 was the first time we were able to calculate an arcing current.
Yep.
And remember, 1994 is when we started talking about arc resistance. So there was a lot of research that was going on to understand arcing. And I can go all the way back to the 1960s and
Oh yeah.
70s when it comes to arcing, right? So
Yep.
what got us
It's
to that whole arc is that realization that overcurrent devices are getting bigger, voltages were coming were going up, currents were going
Mhm.
down, longer clearing times, all that good stuff, grounded systems, and
Yep.
and so now we've got to figure out how to we either try to address and reduce it, or we try to contain it. And this
Yeah,
whole
you and I had a good discussion on this the other time. You were talking a little bit about system design and
yeah,
how the transition from an ungrounded to a solidly grounded to some of the resistance grounding that we see today. I mean,
right,
just that step change in magnitude of available fault current from a phase to ground fault. It's
yep,
You can clearly see the parallels in the equipment design as the system conditions change.
exactly right. And so now we're looking at, okay, now we got to contain this arc. So then you take a piece of equipment that you take this type of equipment, and let's say that it's, forget about the big chutes that are way up there on the top, right? And
Sure.
this is just either a low voltage assembly or a switchboard, or it could be an MCC, whatever the construction would be. You've got a couple different choices. You can try to reduce the arcing currents that are in there to protect the equipment, because now we have a lower current. We've got that three-phase bolted fault current that we have to brace it for. But then we have to say,
Yep.
what happens when an arc occurs inside? How do I respond? I can either try to reduce it and clear it fast, or the other concept is I'm going to contain it and then
Yep.
put these big baffles up on the top and then just funnel that energy up and out.
Yeah, there's a lot of effort in the design of this equipment to try to handle that fault current as well as try to mitigate the effects. I mean, if you think about it, for much of the known science, an arc is a very untamed beast. So
Mhm.
being able to control it and to redirect that energy is a big science in and of itself.
Yeah, and we're doing testing right now in St. Louis, and I was
Hmm.
watching it all week this week, remotely, obviously, and Dr. Lee is watching it remotely, and every arc is different. I mean, you
Yep.
might get one that you get the big bang, and then you get another one that's
Hmm.
not quite as big, and you're like, well, what happened? Well, that's that.
Yep.
No two arcs. And somebody made the statement. I think it was Todd Lottman was in there, and he says it's like snowflakes. Ain't two snowflakes the same? And there's no
Yeah.
two arcs the same.
I
But
believe I've seen in some of these arc resistant type tests, the duration is so long that you'll get an initial
yeah,
boom from the event initiating, and then you'll see a secondary boom, which is actually the air starting to combust as well. So
yeah.
it's a lot of phenomenon.
Yep. Now, and then to your point, when you talk about the concepts of you're going to need to work on this, you're going to have control wire, right? So you
Yeah.
may be able to close the door and just open a door to a compartment that, the way it's tested, like in a 2B construction,
Yep.
the arc won't propagate into that low voltage compartment, so you're protected should something
Correct.
happen while you're doing some work, like I guess that would be this top area right in here.
Right. So basically, assume that in this particular case, that main magnum breaker door would be closed,
Hmm.
but you could see you've got some pilot devices in that compartment. That equipment would probably, if not usually, be tested without that control compartment door above. So that lower door would be shut, but that compartment up there. And the difficulty here is obviously there's a great deal of control wire going from that breaker compartment into that control area. So you kind of have to effectively seal that off so that somebody could be working on that switch or pilot device or those contacts in that area, um, and that equipment is designed so that should an arcing fault occur in that breaker compartment, they're not going to have any of that propagate into that area.
Right. So this big door here would be closed. This top
Yep.
door would be open,
Hmm.
and then you would be working in here. And if a problem occurred, either in this cubicle or any of the cubicles around it, it's not going to
Correct.
propagate through here because, to your point, you're isolating that, and that's what 2B testing is, right?
Yep. Yeah, you're going to see various assessments or what they would call accessibility types. You'll see like a type 1 designation. That was kind of the first wave of standards, basically assuming the front of the equipment is all sealed up. There's no uh, exposure to any of that energy from the front of the gear.
Right.
That was an early on assessment as people were just learning to test this equipment and what they could do from a design criteria. The next accessibility type you'll see is a type 2, which is basically what I call a perimeter driven spec. Basically, front, sides, back of the equipment are effectively designed to contain that energy. And so, in those types of arrangements, you'll see um, test stands located all around the equipment and things like that.
So wait. So type 2
Yep.
is the perimeter. So that's the whole, all the outside of
Yep.
the equipment. Nothing with compartmentalization.
Yeah. Then you get into the next layer of additional suffixes, which you'll see a suffix 2B or 2C, like we're talking about. Um,
Okay.
Commonly, from an equipment side, where you'll start to see those suffixes for Type 2B are going to be in things like low voltage switchgear, as you've got shown, or medium voltage switchgear, or other things that are designed in such a way that the traditional equipment allows for compartmentalization from breakers and other control compartments. So, for instance, in motor control centers, where you're going to see it, you'll see manufacturers stop at a Type 2 because there's really not a compartmentalization between power and control components. They all kind of share the same space with that equipment design.
Okay. So what's the significance of type 1 versus type 2? Is
Type 1, consider it, in some regards, it's called an arcing wall. Basically, the front of the equipment has been sufficiently designed to not have any effects come out the front, but it makes no claims about what may occur on the sides or back of the gear. So you could blow a hole out the back and something like that, and you might get a Type 1.
okay.
Type 2 is basically all around, or what would be normally considered accessible, right? Because this equipment's going to be in a room or what have you, and you might have sides of the gear where somebody could be present. That's really where that Type 2 designation really kind of sets that minimum threshold there.
Yeah. So there's no type 3. So it's type 1 or type 2.
Yep.
And then you have when you talk about a 2C, a 2
Yep.
tells you how it's going to react, that it's not going to blow out the back, all the other good stuff. B talks about the compartmentalization, and then a
Hmm.
2C is suffix C in the standard,
Correct.
and that deals with the effects of an internal arcing fault is desired between all adjacent compartments within the switchgear assembly.
Correct. Yeah, when you start to get into a Type 2C, you got to really start to think three-dimensionally with the gear design, and it's really only applicable to that type of medium voltage switch gear arrangement where if you can think, you've got a breaker front of the gear in that compartment, you've got a main bus compartment, you've got a rear cable incoming. You start to really get into compartmentalizing the design such that faults can't propagate not only above and below or to the left or to the right, but also diagonal as well. So it's a lot more difficult to start looking into that level of compartmentalization.
Is there equipment out there that does a 2C type of construction? Does anybody make anything
Uh,
like that?
You might see some. There's some that exhibit some that might be marked as like a Type 2BC or somewhat of a combination rating because maybe a manufacturer has tested a certain arrangement that has achieved that in a particular area of the equipment.
Okay.
But I don't know that I've seen it. It's probably not as common, at least to my knowledge, uh, where you would see a complete 2C offering out there.
Gotcha. That makes sense.
And you'll see, like within the standard, there's a prescribed table on typical supplemental ratings for various pieces of UL equipment, whether it's an 891 switchboard, 845 motor controller, 347 medium voltage motor controller, and so on and so forth.
Okay, so okay, let's talk a little bit about the arc ignition.
Sure,
The when you if you're going to get a piece of equipment and say that I'm arc resistant, hey Moises Fuentes, good to see you, buddy. Um, when you're going to create this piece of equipment, you're going to create arcs inside. And I did
that's
read
right.
somewhere and we were just talking about it uh, with the testing that we're doing down in St. Louis for
Yeah.
1584. The size of that guide wire, that ignition
Yep.
wire, will change based upon the equipment, right?
Correct. Yeah. So you might see something, for example, in that video that you showed with the switchgear, medium voltage switchgear. You're at a number 24 or 24 gauge bare uninsulated trigger wire for all intents and purposes, and that is placed between all three phases, and that is substantial enough to once you get it going, it can last that entire half a second.
Wow.
Um, once you get into some of the lower voltage, low voltage switchgear, or low voltage motor controllers, um, you get into the size range around a number 10 or 10 gauge wire. Um, and there's consideration given towards, do you get a higher strand count? I mean, ultimately, you want to create the ideal chance of that initiation, and also in some regards, you want, in order for a good valid test, you want the arcing fault to be significant enough, and it doesn't. Once you trigger, and you might see this in some of your 1584 testing, is in some cases the initiation is enough to blow it out, almost like it's a candle, right?
Yeah.
Um,
Yeah.
so in some cases there's an effort to retest. You might not get a good ignition.
Yeah. In fact, like we're trying to identify where you don't have to do an arc flash study, right? Where it doesn't sustain, and
Yeah,
and so we're doing those arcs, and when it doesn't sustain, we have to do it again. We have to do it again just to make sure that that wasn't one of those, flukes. Um, but yeah, I found in the standard where it says a type 1B is it says that arcing does not cause holes in the freely accessible front of the enclosure or in the
yep,
walls, isolating the low voltage control or instrument compartments. And then a 2B says that arcing does not cause holes in the freely accessible front, sides, and rear of the enclosure
yep,
or in the walls, isolating the low voltage control or instrument compartment. So your point,
right,
blowing out the back, I mean, 1B could take the sides out and the back out. You just want to make sure the
yeah.
front's contained.
And
So,
obviously, it gets more critical as you have commonly in switchgear, cable entry and exits are commonly placed in the rear. And so, obviously, that's a very high degree of area why that threshold of a type 2B is kind of seen for those types of applications.
excellent. Okay. All right. So, do you want me to pull up some of the slides, or is there anything you want to speak to over there?
I guess, it would be good. I don't know. There's another video I think I sent. It was one that actually one of the ones we tested. Just to kind of get some comparison even around an MCC application. I don't know if you see that up there.
Is this talking this one here?
Let's see. Yeah, there you go. It's
Okay.
it's a little bit of a high speed video, so it might take a little bit for it to go. Similarly, the one thing, Tom, I always joke, with all these videos, what's missing is the guys in the lab all
Oh,
giddy or watching the.
yeah. And I noticed this one's indoors. It looks like.
Yeah, yeah. I mean, certainly in various test lab setups are set up differently. That one was actually at our test lab in Beaver. So you could see that that's a low voltage MCC and a pass. There's a little bit of you can kind of see there's a test stand simulating there, but very quick um, in terms of the duration there.
Right, and this is a slow motion video.
Right. Yep.
So that's a motor control center. Where's the front? Is it on the left there?
It is on the left, which is, I think, in this particular this one, the initiation was in that front compartment. But as you can see, this is a good side and back view. You can almost see the test stand really all around the equipment at this point.
Okay, the rack that we
Um,
have in front and on the sides, is that measuring, temperature? What is that?
so that's part of the criterion for arc resistant equipment. Um, what we talked a little bit around the initiation, and you've got a different pieces of equipment, different areas of the compartments that you've got to identify and assume as the worst case and identify that. In the setup, you can also see there's a little bit of a wooden building that we've kind of constructed. That's to mimic a little bit of the effect of a room,
Ah,
recognizing that this equipment is, you might have a wall that if that energy goes out on a particular side, especially if you think about some of that switchgear with an overhead plenum, you might have a deformation there.
mhm.
Um, this test stand is part of it. There's about five criterion that we have to test for, and one of the most visible pieces is these black kind of cotton indicators that you see all around the equipment. You
Oh,
can
so
see there.
those square things are cotton?
Yep. Yeah, so it's a metal frame, and if you can imagine it, and then there's certain, type of material, really trying to create something similar to a piece of fabric, and it's really any ember that catches on them, you're going to see the entire square go up very quickly. And they're about a 4 by 4 inch square. And as you can see, they're very tightly configured around the equipment. So basically, this is trying to maximize if there's anything coming out of the equipment and a hot flame or ember catches, ignites those. That's going to catch and identify that was a fail. So
Right.
obviously, in this particular situation, it was all good. Additionally, the equipment that test stand is located about 4 inches away from the equipment there. So
Mhm.
there's a little bit of space. You can have some equipment bowing and denting, if you will, but you can't have it deform enough such that the enclosure doors are compromised, or any of the test stands are knocked over, or things like that. So you're really you really got to hold that energy in, from an equipment performance standpoint.
Gotcha. That's pretty cool. So the whole and I think this is a part of my, my personal love-hate relationship with the whole concept of arc resistant is it it's good and it prevents that, like you say, when there's an internal fault, but from an electrical worker perspective, it really doesn't do much for that person outside of now granted, I can't really say that knowing now a little bit more about 2B
Yeah.
that there are accessible areas in this equipment that the
Hmm.
electrical worker can expose himself to, say, lower voltage in those compartments and not worry about if there's an arc flash somewhere in that equipment, that
Yep.
they're going to be in harm's way. So that is a little, this little session right here. Up until this moment, I mean, I was always, I'm serious. I would be like, guys, this does nothing for the electrical worker, and I can't say that anymore.
Well, and I would say too, additionally, what you'll find is in addition to having this type of testing criterion for the equipment, obviously manufacturers, in order to get a successful pass in the equipment, you could almost consider, we want to effectively deal with that internal arcing fault. In some regards, that's looking at areas within the equipment of where an arcing fault might be initiated and finding a way to insulate it, right? We don't want that arcing fault to last very long because the longer it lasts, it's a much more complicated design that you get into it. And in some cases, as you look at arc resistant designs, the use of various barriers to isolate between compartments, like we're talking about, between vertical sections, are usually applied as standard because it helps the equipment perform in those types of scenarios.
Yeah.
So a lot of the features that maybe a standard piece of equipment might consider as optional, if someone was looking at one feature or another, a lot of times in the arc resistant construction, it might be a default. So you're probably going to see things like insulated bus, even on a low voltage side, applied as standard, um, and a lot of efforts to try to mitigate that effect. There is a phenomenon, outlined in the standard that talks about, again, this concept of self-extinguishing, where the equipment is designed effectively enough that even if you initiate an arc in this area, and you have this prescribed duration, there are certain situations where an arcing fault will be cleared by the equipment at that point.
Well, yeah, I had someone else. We were talking about the testing we were doing down in St. Louis on arc, for whether or not it will sustain itself. And the um, the individual I was talking to, he says, we're not doing the testing, which is true, on equipment. And his
Yeah,
point was that if you did do the testing in real world equipment, which there are a lot of IEEE
yeah,
papers that show this, there's a very good chance that it's going to self extinguish anyway. And
yeah,
so, but
it,
again, the testing that we're
yep,
doing is establishing a worst case scenario
yeah,
so that you'll probably be overdressed for the situation. So,
yep, yep,
but that is what it is. All right. So we know we have a piece of equipment that is contained. It contains the arc. You have
yep,
to reinforce all of the hinges, and I know I
yep,
had pictures, I think, of that to help demonstrate the
yeah,
like on this one here. There is a there's this gasket. That gasket helps
yep,
contain and seal that arc
yep,
in.
yep,
You've got the foam, and look at the. You could just look at the beef on a lot
yeah.
of these that you wouldn't see that on standard equipment, right?
No, you might see something, a very simple quarter turn latch, and so obviously one of the main things is that we keep those doors closed. So very common area to focus in on is the rigidity of that door, whether it be on this side, like we're looking at with the latches. On the other side, it's also the hinges, right? You
Right.
don't want those pins to roll out and things like that. And then obviously the care made around the frame of the breaker here, so that that bellows is going to seal off that front of that breaker.
Yeah, I'm just looking to see now the the steel that's used is it the same thickness of the steel in general?
In general, manufacturers will typically have to go to a thicker gauge steel across the board in equipment. Where it might be, a single, going from 12 gauge to 14 gauge, or vice versa, um, 14 gauge to 12 gauge thickness. Um, that provides a lot more rigidity, where things won't want to deform.
Right.
It's a very common design characteristic. Now, again, to your point, if you could achieve some clearing time from faster interruption of an arcing fault, you might be able to achieve the same sort of arc resistant rating utilizing standard equipment.
Ah, that's a good point because like we have
Yeah.
the arc quenching technologies, right?
Yep.
So our arc quencher, if I have an arc quencher in there, then I might be able
Correct.
to change my construction a bit because my arc
Yeah.
quencher takes care of the energy and all the forces.
Yeah. Think of the design really being a symptom of how a manufacturer had to deal with that type of energy that was built up. And a lot of the designs can vary, but these are going to be common attributes that you see, but certainly don't always apply.
That's a good point. And I know I had a video of our arc quencher in action. If I can find it, I will. Um, and I know there's some videos online as well. And I thought I
Sure.
downloaded those, but I don't know if I did or not. So okay, so I can Oh, and there's another thought process because I was just doing a program today with Justin Caron in the healthcare segment, right, with Ashy,
Mhm.
and we were talking about designing for safety. And what we did was we said you have the design phase, you have the installation phase, and then you have the ongoing phase where it's growing the facility. And we talked about somebody asked a question because we talked about putting things in the beginning, like if you don't, for example, if you don't buy an arc resistant equipment, then it's not like you're going to say, hey, down the road, let's convert all of this stuff
Mhm.
over to be arc
Right.
resistant equipment, right? Because
Yeah.
because you can't change the whole construction of the installation. I mean, it's not just
Right.
about hinges.
No, this is definitely one of those ones that needs to be planned in the upfront design phase. Now, granted, the equipment might be designed for expandability, but obviously each of the equipment lineups are tested and built around a certain configuration. It's not
Hmm.
a add a couple features and you're good.
Now, Joe Bellantoni wants to know: is the gasket treated to withstand the heat?
Yeah. So again, the main criteria you're going to see in arc resistant, there's 5 areas. The gasket is really how we handle that is kind of in the science with how we achieve that pass. But I mean, ultimately, we're identifying a material that allows us to seal up that compartment. We're not going to allow, even one of the criteria is particle size. You can't have anything greater than 60 grams, which is a really minuscule amount of material come out of the equipment. You also can't, as we talk about, get any of the hazardous arcing energy out of that equipment such that it would ignite a burn indicator. So, however we achieve that, whether it be with a certain type of gasket or things like that, I mean, that's just behind the design. But really, the ultimate goal is to meet those criterion.
Right. And
Um,
and and you run the tests with these gaskets in place, and that material can
mhm.
withstand the temperatures that it's going to see for the
Right,
duration that it'll see it.
right,
And now, whether or not it probably is a special, recipe
right.
from a gasket perspective that we special order for that application.
Yeah.
But all right, beans. Okay. So we got the duration. We got the. Let me just look and see if we had future proof your equipment. Absolutely. Let me just look. Blowing things up. We got. We were dumb in the '90s. I don't know if we were dumb in the '90s. I would say we were probably. This is a thing about safety and solutions. We can
Mhm.
identify that we have challenges with something, and then all of a sudden, someone
Yeah.
comes up with an idea and an invention, and it
Yep.
changes how we do business, right?
Yep.
So we have new technologies today. We have new technologies. We'll have new technologies. 50 years from now, people will be
Mhm.
looking at what we're doing, going, "Would you believe this is what they did?"
Yeah.
And we think it's state of the art right now. So
Yeah, I mean, it's definitely a symptom of, like you said, there's new technology out there, new ways of looking at items. I mean, you look at it now, even in the automotive industry, there's so many safety features that are on equipment now that, even those lane departure features, it's not that we're any worse previously. It's just different way of thinking about how we approach safety.
yeah, absolutely. So we talked about the 2B and 2C. Um, all right. So where else? Where's our next part of this journey?
I don't know if we got into all the various criterion. I know we
Yeah.
focused a little bit around uh, the indicators as well as the distortion of the equipment as well as the particle size. But there's a couple other ones that might be good to talk through. There's a topic around burn through.
Oh,
Um, so commonly within electrical equipment, where we mount the bus bars, you might be in close proximity to like the sheet metal or the enclosure, right?
yep.
And so in some cases, you have to initiate an arcing fault right where those phase bars are, and you can't have that arcing fault burn through the equipment such you got a hole in the gear. Um, so there's an assessment around that. So in some cases, you're either uh, providing more insulation there, an air gap, or a larger distance there, or making sure that enclosure is sufficiently designed such that it doesn't burn through during an arcing fault.
So
Um,
so
what?
so what you're saying though is you have this big gray box with all this stuff in it,
Yep.
and
Yep.
and from a standard perspective, you have to look at the construction, and they'll
Yep.
tell you where to initiate faults,
Yep.
and then
Yep.
you have to pass the standard criteria of not burning through. So you find those
Yep.
places where you're close, and you have close, like from a bare bus bar to the any
Yep.
types of parts of the structure, and you initiate an
Yep.
arc there.
Yeah, exactly. So, if you think about it, commonly, whether it's a switchboard vertical section or an MCC, commonly that equipment is designed for expandability, like we were talking about.
Yeah.
Those are areas that you've got to really look at to make sure that that arcing fault, if it occurred there, um, doesn't burn through that equipment.
Gotcha. Gotcha. And that's and so like, well, obviously you can't test equipment over and over and over, right?
Right, right. There are conditions where you might have a duplicate test, like we are talking about. If your first initiation goes out prematurely, you'll have to test that again. Additionally, some of the survivability of the equipment is valid enough where it again clears it, and you've got to test it again. Um, there's another area where second testing is common, and that's in the description of things that are called duration rated versus device limited. And the topic of device limiting actually, or device limited, gets into the topic of when you have equipment that is supplied by current limiting devices. And in that case, they're looking at, well, you might want to test that equipment at, say, 65 or 100 KA, right?
Hmm.
Um, in that application with a current limiting device, that's going to be way below on in terms of the maybe the maximum amount of energy that that equipment might see. So you would actually have to go back and you might have to first test it at that maximum threshold, but then you would have to take a second test and test it right at that knee before it becomes current limiting, to see if it's any worse of an energy present.
Wow. Okay.
So
Must.
device limited is very prescriptive in terms of current limiting fuses, current limiting or molded case circuit breakers with current limiting characteristics, um, and a lot of those times, again, you'll see duplicate tests created just to evaluate the two different points.
So when we talk about current limiting, though, the it's only current limiting when you have these high fault currents. I mean, what's the evaluation done for the very low fault currents that would result in a very high, long clearing time?
Yeah, it's mostly focused on that high end. Like I said, with the current limiting, they'll look right at that point before it becomes current limiting, and that's the assessment. Anything below there, I believe, is really outside of that scope.
Okay.
Right? You're focused on that high end of that initiation of the arcing fault. I think there becomes an issue of at the lower the magnitude, or you're actually do you have enough available to actually drive an arcing duration, right,
Right.
for that amount of time?
Okay. All right. So we hit the Y arc resistant. I mean, that's containing
Yep.
and that's expanding. Well, like what kind of equipment? So I know low voltage assembly, medium voltage equipment, definitely, right?
Yep.
Um,
Yeah. So initially, this again, as we talked about earlier, this was built primarily first for medium voltage switchgear, but through the years, there's been a lot of additions. Um, the last I'll call it not this latest update, but the previous one included things like low voltage switchgear, basically applicable to all. But then this most recent update added things such as motor control centers, switchboards. I believe there's a discussion around bus duct as well. Um, so yeah, there's a lot of different equipment types now supported in the standard.
Now, how they do that in the standard, you have the general requirements up front,
Correct.
and then when you start to get to the special equipment, they do those in annexes, right?
Yeah, you're gonna have an overview of the basic parameters of the test setups, and then they'll point to the various equipment annexes. Really, the main difference you're gonna see is a prescribed what is the preferred arcing duration for that type of equipment? Um, what is the ignition trigger wire size? And also pointing out areas of the equipment that are needed to be assessed for each different type of equipment.
Right. So if I look at this, like Annex D is your metal enclosed, low voltage. You have Annex E is metal clad switchgear. F is
Mhm.
metal enclosed interrupter. G is outdoor equipment. And then H is motor control centers. You know all about H.
Yep,
Medium voltage AC controllers. So switchboards is Annex J. So they have all the different types of equipment, and the reason that's important is because the initiations will be different. The construction is different, right?
correct. Yeah, and so the placement of, trying to cover the various arrangements of that equipment and how it is commonly designed, you're certainly going to have different areas to focus in on in terms of performance of that equipment. Um, we talked a little bit about duration, but you know, in a switchgear application, whether it's low voltage or medium voltage, that equipment, uh, as it's listed, is a 30 cycle or half second product. So its arcing fault it lasts that long, but obviously in a low voltage switchboard or more control center, we're much lower on the voltage fault or short circuit current rating in terms of duration. And so you're going to see much shorter arcing duration times for those
So
pieces of
when you say
equipment.
duration, you're talking like you that's 3 cycle equipment, right?
Correct. So a switchboard, UO 841 or 891, 845 MCC, that as it's described in UL is going to be a 3 cycle product or um, 50 milliseconds, right?
Yeah.
You go into a motor control center assessment for arc resistant, you're going to find a preferred arcing duration actually at 100 milliseconds was the agreed upon duration there. A little bit higher in terms of duration than what the bolted fault rating, but certainly meaningful enough for that type of equipment.
Yep.
You
I think
go into the annex for switchboards, I think it'll be at that same 50 milliseconds.
Yeah, I think a lot of people miss that about equipment is they look at that three-phase bolted fault current value, and then when we
Hmm.
start applying overcurrent devices, especially and when you're doing coordination and things like
Yeah,
that, you're putting intentional delays in,
yeah.
and now you're letting that fault current flow for more than 3 cycles, which is outside of the rating of the equipment.
Yeah, that's I think one of the things I've noticed too with the all the effort around arc resistant equipment is now all this equipment now starts to have different duration times, and as you mentioned, it kind of reignites that active debate around delay times and coordination, as well as the equipment ratings. Right? It's
Right.
some like you said, it's an often overlooked thing that is not as visible at certain times.
Yep. 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 Okay. Where's my notes? So we hit the different types of equipment. You're not going to get an arc resistant panel board, right?
I don't believe so, no, at
Yeah.
least not yet.
Not yet. That's right. Not yet. Um, we talked about the whys. We talked about the types and the class, types of equipment, the testing criteria. We talked about the burn through.
Yep.
Do we need to talk anything more about the testing criteria? Now, Robert was asking about angle and magnitude and sequence have a part in design. I'm not sure what he means by that. Um, but closing angles and whatnot, we take the worst case closing angles for the power factor, right? Of the
Right.
when we do our test. So we always take that worst case that we can.
Mm,
We talked about
equipment grounding.
oh, that's right. That I knew there was
Yeah,
something in there. Equipment grounding. So the bonding and the
yeah,
grounding of that equipment has to stay
right.
intact
Yep,
after the event.
yep, absolutely. So you've got in the various equipment that is grounded, you've got bus bars that are grounded, and so, um, should that bus bar be mounted with sheet metal screws or things like that, um, an arcing fault can very easily eat through
Yep.
those screws. And so you may have to ruggedize that in order to maintain that continuity and grounding system for that equipment.
So I can't have burn through. I have to
Mhm.
maintain the integrity of the grounding and the bonding. You mentioned this. Um what about I don't know what they call what would you call it? Deformation or like my equipment, the structure itself. Can I have the
Right.
doors bow out or anything like that?
You can get some, deformation. Obviously, you still have to maintain the integrity of the latch and hinge and things like that.
Right.
Um, you can't get enough that it's, starting to compromise the enclosure, i.e., you can reach into it and things like that. In some of the cases, like the plenums that you see in some of the medium voltage switchgear that are overhead, that equipment is actually kind of designed to absorb some of that energy. And so what might initially look like a square duct above that equipment. After an arcing fault, it looks like a balloon. It's all bowed out and things like that. And so you'll actually see, and it's a good installation note, that a lot of those equipment designs, not only will you have to consider overhead clearances for the gear and what have you for cable tray, but also the amount of what might be anticipated from a deformation of that plenum.
There's
Um,
this is an interesting discussion because I'm just sitting there thinking there's nothing there's nothing in the National Electrical Code that talks about the installation of this type of equipment to handle, like, for example, we saw the
yeah,
top. What do? We vent it up and out, right?
right.
There's nothing that says I can't vent that up and out into the next room.
Right, and you'll see various plenum designs, where say you've got a medium voltage switch gear that's close coupled to a medium voltage MCC, and you might have a common plenum, and you're going to have various ducts to route that energy outside of the equipment. That could be routed outside of the building or to a prescribed area. Um, Fortunately, actually, for our MCC application, we're actually able to achieve arc resistant criteria without having to do overhead plenum. So it is possible. I think you've seen that also in the arc quenching switchgear. One of the other side effects or benefits of that device is that it actually greatly reduces that requirement for an overhead plenum to be incorporated. So that's one of the unique things about as we advance from a manufacturing side, we can start to achieve some of those same sort of creature comforts that we're used to. Um,
Right.
Not all equipment, but certainly some can achieve that.
Yeah, I was just looking to see, and I might be up. I might have to call it up on YouTube, but I could have swore I had the arc quencher stuff, but I don't think I do.
Yeah,
Anyway,
I think I sent you a little slide that kind of shows a little bit of the MCC arc resistant types. We could actually pull some pictures up from that as well.
yeah. So this is your C, and again, it's I. We didn't even say that. It's IEEE
Oh,
C37.20.7.
yep.
Geez, oh man, here I am. I've got the standard opened over here, and we never even talked about the IEEE standard number.
Yeah, yep.
Geez, now it's an IEEE standard, but is it UL listed as arc resistant?
No, you'll actually have you'll work with entities like UL or CSA or whomever as a nationally recognized test lab to assess the equipment. There certainly is some considerations as do you look at various listing of this, or in most cases, what you'll see is more of a type assessment of various equipment configurations looked at.
Right. Okay. So, okay, so you will have a UL label on it, but it'll be listed
Correct.
to this IEEE standard.
Correct.
All right. So it's C37.20.7, and oh, it was updated in 2018. Mine says 2017. Is there a newer
Yeah, it
version?
came. No, no, no. It came out really towards the tail end of 2017. I
Okay.
think it actually didn't get published online until 2018. So uh, I just recall the timing on that. And this was kind of the criterion that we walked through. So we're pointing to various scaffolding, some of the arrangement, as you can see, around the equipment. These were the various criterion we talked through.
Right. The video that we saw, um, was it this equipment here that we were looking at?
Yep. Yeah, this is just a different angle of that same
Okay.
similar type of test setup.
Okay.
Uh, Other thing of note is kind of interesting if you think about it. Um, typically motor control centers are 5, 7, 10 sections long, right?
Right. Right.
You notice in a lot of these test setups, you're dealing with maybe 1 or 2 sections, largely trying to minimize that amount of volume. The more you add vertical sections, the effects of this start to diminish pretty quickly. So the worst case is usually those single section arrangements or 2 sections.
Well, and yeah, and it's and you're not giving that arc anywhere else to go inside. You're
Right.
containing it, so it's got to come out. So
Yep.
I get that. I get that.
And in some cases, what you'll find, and this is maybe a little bit prescriptive around our capabilities, but there's a little bit of detail I think on the next slide that talks a little bit around like the various hardware. Maybe not this one, the next one, where this talks about the sheet metal. Um,
Okay, so
yeah,
this is showing you that
yeah,
this was the question I had earlier,
mhm,
that the gauge of the metal is going to be thicker,
yep,
and I didn't know that 12 is 40% thicker than 14.
yeah. You wouldn't think it, but it's
No,
and quite honestly, we've got considerations around. Do you have to mark that sheet metal differently as we're producing it in the factory, right? Because it is much more. It doesn't feel that much, but it is enough. But here's
right.
what I was talking about earlier too: is in some cases, as manufacturers, we're looking at ways. You've got insulated horizontal bus. You've got barriers between vertical sections. Um,
That's right.
Insulated vertical bus. So I mean, we're really trying to create an environment that isn't conducive to an arcing fault lasting.
So
For our
that's
own,
what these barriers are here.
right? Yep.
Okay. And then now this insulation, that's again, that's providing that protection. That's insulating the bus,
Yeah.
and that's, do we do that to pass the test, or do we just do that? I mean, I've seen this type of insulation even
Yeah.
in non-arc resistant.
That's correct. We apply that in non-arc resistant equipment. When we get into arc resistant equipment, we apply this as standard.
Okay.
We recognize the benefits of that type of insulation medium, and certainly does a lot to help with some of the self-extinguishing capabilities.
Okay. Okay. So here's
Yeah,
this is a good. There's your
yeah, there you
difference
go.
in latches.
Yep. Yeah, and in some cases, some manufacturers you'll find that, one will have like a male latch and then a receptacle on the enclosure. The way we achieved ours is with a simple, quarter turn latch. But as you can see, it's a lot more beefed up. There's a hook that engages into the framework so that it's got a very tight hold. Interestingly enough, the latches are actually on there's a spring there, and so during the actual event, that spring actually somewhat helps burp the equipment, if you will, from some of the pressure buildup. Obviously, not letting out a significant amount of energy, but enough that the equipment's still performing, right?
So have you burped your gear today?
That's right.
Jeez. Burp your gear. Now what, now this is okay, this is your, now you can see this is it's much more now I know whenever you see in metal that press of a V, instead of a metal like
Mm,
this, if it's pressed like this, that adds
yep,
strength, right? And
yep,
rigidity.
yep,
The other one on the right doesn't have it, probably because it's much thicker material.
correct.
All
Yep,
right. So the steel is thicker, all of the hinging material is thicker. There's barriers in place that you're not going, I mean, this
yep.
really puts a nail in the coffin of, you're not going to do this to an existing piece of equipment. 4-inch sections installed at each end of the lineup. Why do you do that?
So if you think about it, whether it's a switchboard or switchgear, we're all relying upon a metal framework in the equipment. So if you zoom in a little bit, um, you might see some of this. If you can imagine, there's a couple things that we're achieving. One, we talked a little bit early on, Tom, about burn through.
Yep.
Remember where our horizontal bus bars are going to be adjacent to that enclosure, so we're actually giving a bigger air gap there.
Ah,
Additionally, we're actually helping to bolster that framework of the MCC, so it kind of gives it more of a, call it a, bookend, if you will, for bookshelf to really give it support on the end of the lineup. So you'll see that on either end in our particular design in this
okay.
case.
And everybody will be different, to your point.
Correct. Yeah.
Right. Now, I don't I'm looking at this, I don't see those big rubber gaskets around this bucket. Why is that?
Fortunately, again, in our testing, we've got some rubber gaskets that you'll see a little bit there, but as you can imagine, a motor control center bucket is pretty confined space, and with the addition of the latches and things like that, this is again the design of the equipment varies by manufacturer and even with the type of equipment, but again, that criterion of how you're passing it, can vary from time to time.
Okay. Okay.
So yeah, there's nothing that prescribes you have to use a particular type of gasket or things like that. Your main goal is to meet those type of withstand and various criterion that we talked
And
about.
those are all
How you
performance.
Yep,
Yep, that's all performance criteria. So however you need whatever you need to do to the
yeah,
equipment to pass the test, that's all you need
yeah.
to think
And
about.
I think this is a bit of another discussion point too. I think there is a perception out there on arc resistant equipment that it has to look like XYZ or has to have these sort of features.
Hmm,
But to your point, we're given a performance criterion. How we achieve that, that varies from application.
right.
So yeah, we were fortunate enough to achieve ours without having to do an overhead plenum or roof lap. So we've not been able to uh, get a fault that lasts longer that we have to vent it somewhere. So
Oh, so that and that's what you're talking about. Since you've got all the barriers in, you've got the insulation, and the arc itself won't sustain itself, so you don't have to
correct.
worry about venting it because if you when you
Yep.
cause an arc, it won't. Which is the point that was made to me earlier when we're doing
Yep.
these tests in a lab, not in equipment.
Yep.
Based upon the construction of equipment, I could get significantly lower incident energy for the electrical
Yeah.
worker. I'll calculate a number, but it will be significantly lower because of the
Yep.
construction of the equipment, and it won't sustain itself.
Yep. Sounds like we need to make a trip up to St. Louis there.
We should, and you know what? And I know I've seen papers to this point, but here's
Yep.
what I'm thinking is, in some cases, I might be able to say, yeah, this is your arc flash calculation. This is what you'll get. But if you use my equipment, I have it certified that the energy that you'll see in here is not going to be greater than a certain number because of the
Yep.
construction parameters.
Yep. And I think the last part is actually a pretty good segue. You know, I think you were talking a little bit. Is it the whole solution, right? This is probably a good discussion point. There's so many different other features that we have available to us now that is this everything, right? You mentioned a good point. It certainly um, does prescribe that doors are latched, secured, equipment's properly maintained, but what other areas of the equipment need to be looked at as well. Obviously, we're doing what we can to build up the equipment for that, but there's a lot of other avenues to go down
Yeah,
for overall safety.
yeah, absolutely right. So you want to prevent it from happening. You want to make a safer structure, safer unit, incorporate the communications, the diagnose, and then there's the presence of voltage. And so we're doing all these other things. To your point, we can get the electrical worker out of the bad, out of the arc flash boundaries.
Yep.
We can remotely operate things. We can remotely monitor the condition of things. And I think Robert made a point of maintenance to make sure that we're performing maintenance and the moment you open certain compartment doors, and that's the other thing is you got to really be trained to understand what doors you're opening and what your exposure is.
Yep.
because you opened the wrong door and now you've defeated the arc resistant nature of that solution. I
Yep.
might be able to address lower when I open up the control panel, the compartment, because I know nothing's going to crouch into there. But if I opened the wrong door, that would be ungood.
Yep. Yeah, and I think early on in this presentation, we talked a little bit around, various types of equipment that were involved in electrical accidents or incidents. Um, and one of the areas that we always kind of focus in around is certainly around motor control centers, control panels, and things like that, where there's a high degree of interaction with that equipment as it's assigned to a process or things like that. And so, it's really being cognizant of what the equipment does, what it's designed to achieve, and when and where those things are valid or invalid.
Right. Right. So I think my major takeaway from our discussion here is arc resistant equipment contains the arc flash. It can help the electrical worker who might need access to low voltage compartments, and with the technologies like presence of voltage indicators or even those ports, I could pull ports out to do
Right.
some limited testing outside of the equipment, and also you've got those the capability to keep the door closed and
Yeah, that's yeah, and be able to rack it out, right?
yeah, so
This is
you
actually one of the things that you'll see in NFPA 70E. Um, if you have arc resistant equipment construction and you have an ability to rack a unit out from a motor control center, your likelihood of exposure greatly decreases,
that's right.
right? Because all the doors are completely secured, and you're removing it from power. You're not likely to experience exposure there.
Yeah, so you can take this entire bus via this unit where you have this arm. Now, um, this is where, even this activity, I know we got the doors closed, but and we're going to talk about this on Tuesday next week with Russ
Hmm.
Seyfried about how we can do things away from the front of the equipment. So even though this is
Right.
normal operation, I'm racking this off, I've got the doors closed. I probably could put a motorization piece on the front of this and get myself out of the way. And then I'm
Yep.
taking that MCC bucket off of the bus,
Yep.
or I'm putting it on the bus and I'm just adding that additional layer of the onion to say, look, I'm still going to be away from it, even though I have arc resistant equipment. I just don't want to be in front of it. I
Yeah.
mean,
I mean, to be quite honest, too. I mean, there's an area even in the choice. We have starters and drives and protective devices, right?
yep,
Um, the conditions in which somebody gets in often is related to a troubleshooting scenario. And if you begin to think about the choice of motor protection, where you've got relays that have localized HMIs and things like that, that allow an operator to see what's occurred, whether it be from a trip unit or an overload or a drive. You're giving them the ability to interrogate what's going on without having to get into the equipment.
that's right,
You hear time and time again, we're trying to do things without having to get into the compartments. Even this topic around intelligent or smart gear, right? There's a high degree of affinity to even thinking about why you might want to see that information, and as you mentioned, operate it remotely.
right.
Um,
And I might be able to give you information that tells you that you're going
right.
to need to pull maintenance on this
Yep.
specific cubicle because I'm monitoring the temperature. I'm giving you the
Yep.
information that you need to say, okay, I got to think about that cubicle, not these other ones. And that was another part of my discussion on that ASHI program today was the more information that we can provide for the maintenance person, the more they can focus their
Yep.
efforts in those areas of the facility that need it as opposed to doing needless stuff, right? So
That's right.
all of that additional information, all that additional technology, there's our remote capability right there. So you can
Yep.
put that umbilical cord, walk out of the arc flash boundary, press the button and have it rack that in and out off the bus. And uh,
Yep.
25 feet away. What if I want to go 26 feet, Matt?
We'll get a longer cable for you.
Oh, I thought maybe you're going to say we'll get somebody with longer arms.
No.
so, so yeah,
What sort of what
yeah.
sort of questions you get out there with arc resistant equipment? Any other ones come up that you've not seen, or
Oh, and say that again.
any other questions you've seen out in the industry in terms of confusion or concern around arc resistant equipment?
Well, so I always get that the questions I see are related to, can I take the doors off? What can I do on it? How does it help the electrical worker? And then
Yep.
and you know my and before today, which now I'm feeling a lot better about, there are some things the electrical worker we can provide for the electrical worker, but the moment you got to take the doors off, now you're getting into
Yep.
and the other thing is like what David Engelhardt he's asking. He's in late, David. I don't know about you, buddy. Jeez, and then also and the other question that came in it was similar, but it related to the 24067 and 24087, which
Oh, right.
Tamaki even admitted in the email when I got the question that it's not related to an arc resistant piece of equipment, um, but it's related to the testing required for
Yeah.
24067 and 24087. And the question says, do consumable arc energy reduction devices, say fuses or the arc quencher, get wasted in the first performance test? And Tamaki and anybody else out there, I mean, you don't have to damage the equipment to perform the test. And that's why in 240, now David Engelhardt, this was not meant to be about 24087 and 24067. I am addressing this question, and the reason I'm doing that is because you brought this up. But we'll just summarize this I do want to touch about the codes and standards, which we will do in the next call with Jim. I think Jim Dollard is going to help us with that one. But in any case, when you're testing doing the performance testing on first installation for a 240.67 or a 240.87 requirement, we specifically put in there to follow manufacturer's instructions or to primary current injection testing, because there was a realization from the panel that I mean, our busman
Yeah.
fuse guys would love you to test every fuse when you first put it in so that they can sell you another one, but that's not the intent, and that's not what we want you to do from a code perspective. You
Yep.
can test these technologies without damaging it. For example, the arc quencher. There are certain procedures, and we have equipment that we will put light sources at various locations within the equipment. It will generate a small amount of current, but it won't fire off the arc quencher, that blue box that you have to replace it. But it'll test all the different components to make sure that they're all
Yep.
functioning correctly. So, Tamaki, you don't have to, and you are accurate that it does not directly relate to the arc resistant equipment session. So, perfect. That means I've had some people confuse that before, and I know that Tamaki
Yep.
does not confuse that. You don't need to replace those fuses. And NHZX boy says no fuses to replace needed. Indeed, love that. Yep, but our busman guys don't. They wish you would just keep testing those fuses. Um, so and then so I hopefully that answers that. Now, David Engelhardt, what we're discussing is and what this whole program is about is the arc resistant equipment, which contains the arc. It's not addressing the aspect of reducing the arc flash like what
Right.
a 24087. You could still have a 40 cal event, but it'll be behind the steel, right?
Yep.
We're going to contain that, and for his benefit, let's take a look at again a no pass
Yeah.
for everybody's benefit. Let's take a look at this. This is again a trial that does not pass, and what we're saying is we're not going to reduce that energy. in this arc resistant equipment. What we are going to do is we're going to be able to take that energy and make sure that we funnel it up. It's the same amount of energy. If that was a 40 cal event, that was still a 40 cal event, but we're not letting it come out the front of the equipment. And to your
Yep.
point, Matt, the sides, if it's a type 2, I can't come out the
That's
front,
right.
the sides, or the back. I can vent it up the top. Or to Matt's point, if I address, if I construct my equipment such that it won't sustain the arc, I won't have to vent it out at all.
Right.
Right?
Yeah.
So arc, so in that case, and in my, Matt, I mean, and I know I've had this discussion with our engineering leaders and whatnot that said,
Yep.
look, we're doing this testing. We do these arcs in a box down in St. Louis, and we're
Mhm.
doing that today, this whole week. And I'm watching the videos, and we can see that energy come out. And what's playing in my mind is that we can construct equipment that it doesn't function that way. You're
Yep.
not going to see this energy because you
Yep.
you showed us the way we insulate bus, the way we put barriers in there. You
Yep.
can't sustain an arc in some of this equipment, so you won't need these vents like we're seeing in this video because
Yep.
it won't persist.
Yeah, and I think you hit it. It is such a performance-driven standard where here are the ideal being the worst case example of what is agreed upon. This is a worst case trigger initiation. Uh, these are worst case locations in various types of equipment. You have to deal with that as a manufacturer, whatever equipment you're looking at, and make sure that you don't let any of that escape from the equipment in the areas that you prescribe. Type 2, right?
Right.
How you achieve that, that's where it gets into you could, as a manufacturer, minimize that effect and everything, but you're at least guaranteeing that you're not having that come out of that equipment.
Right.
So,
And to your point, I can, like in our arc quencher technology,
mhm,
I could put technology in there that quenches that
yep,
arc. And I could
yep,
put very light doors. I don't have to enforce the hinges. I don't need the rubber
yep,
gaskets because if a fault happens inside, it's gone. It won't
right.
persist. Or
This is this is a completely, entirely different but focused effort on a stress test for equipment, right?
right.
You know, um,
And
you've
and
got to hold up.
Yeah, and I think that's, remember I said it earlier, and I think one of our attendees when brought it up that like back in the '90s, were we dumb? Were we
Mhm,
ignorant of things? No, we thought we had state of the art back then, and we think we have state of the art today. But the future, 50 years from now, we might be looking back and watching these videos going, "Oh my gosh,
right.
look, they're happy with that performance." Right?
Yep,
They're going
yep,
to, so 50 years from now, it may be that all equipment can't sustain any arc whatsoever, and then 1584 and all those arc flash calculations are like, that's for old stuff, not for the new stuff, because you can't get
right.
that in the new stuff. So and I think that's a part of ours, changing our
Yeah.
safety culture, changing the how we make business, how we design systems, and
Yep.
our industry does not accept change fast.
No, it doesn't.
It does
Yep.
not accept change very fast. We don't like change.
At least not until 3-year cycle increments.
Yeah, even then, I mean, even then, we look at 3 years and we go,
Yeah.
it's some. I've seen some ideas. For example, surge requirements. I just had
Yep.
Jimmy on when I gave him his Buck 41 Club Award, right? So,
Dang.
and and we talked about the fact that he was putting public inputs in for
Mhm.
surge on
Yep.
residential dwelling units. We had the data, and everybody poo-pooed it and it never went through, and then all of a
Yep.
sudden in 2020 everybody's like, well, of course should put
Yeah.
surge on these. You know what I mean? It's like,
You saw the same impact on barriers too, right?
oh,
Service
absolutely.
entrance too. Yep.
Yep, and that's expanding, and then in the 2023 cycle they're saying, hey, what's the difference between the secondary of a transformer anywhere in your power distribution system and a
Yep.
utility? Service
Yep.
entrance equipment. Other than having to call the utility to turn something off, you still have the same incident energy issues. You have the same barrier issues.
Yep.
So now they're looking at putting barriers
Yeah.
on that first level equipment on the secondary of a transformer.
And there's a good discussion point. As manufacturers, right, we're adding a lot of barriers to enhance isolation from energized compartments, right? We're putting it over terminations and things like that to prevent incidental contact, right?
Mhm.
The challenge is at the same time, there's also a desire concurrently to monitor those types of connections. Um, how do you make sure your infrared accessibility to those terminations so you kind of have counter opposing forces a little bit? And when some of these arc resistant designs, you have to test um, with the intention of an arc resistant or performance being met with the IR window being on that cubicle,
Oh,
right?
yeah.
Um, so now you've got that feature and put in place, and you've got to consider any barriers that you put in there. Now I've introduced a feature to enhance the usability and maintainability of the equipment, right?
You know what?
Um,
That brings up another good point that so if I
yep,
want an infrared window,
yep,
I can put it in
yep,
arc resistant equipment, but it has to be tested with it. So that means
exactly.
now let me ask you, if I have arc resistant equipment in the field and then want that window, can I do that in the field?
Now you're starting to get into, was it ever evaluated like that? And if so, did it have a certain type of IR window that was looked at? Motor control centers, one of our challenges is we mount a great deal of pilot devices, displays, keypads, things like that that we all have to evaluate. Even commonly, you might see like a little reset button. Turns out a lot of those reset buttons are larger than 60 grams, and so you got to make sure that those things are secured properly and what have you.
You don't want to blow
Um,
that button across the room.
right, right. So,
Wow.
yeah, I mean, it's that little next level of consideration. In some cases, right, we're bearing off. You've got a barrier on. You've got a rear door and then a barrier. But somebody wants to look at a connection that's behind a barrier, and now you're dealing with from a maintainability standpoint, how do you give them an ability to identify and know when they need to service equipment, maybe to retighten bolted connections and things like that,
Yep.
um, while still employing those barriers? And in some cases, the desire to have a Swiss cheese counter opposes the benefit that we get from that very careful, thought out barrier and isolation.
Yeah, you're right. It's very important. I mean, especially, I mean, we always talk about anytime you modify equipment in the field, you need to work with the
Hmm.
manufacturer, you avoid the UL listing, the warranties, all this kind of stuff. But when you have arc resistant equipment, it's even more important that you don't
Yeah.
change any. I mean, you don't even want to
Right.
change, like if an indicating light is not working correctly or a push button is not working correctly, you just don't replace it. You talk to the manufacturer and make sure you replace it
Right.
with the right components, right?
Yep.
That all
Yeah,
makes a difference.
you don't want to just arbitrarily be punching holes everywhere. I mean,
Absolutely.
manufacturers will detail out, how conduits have to be prepared. Different pieces of equipment require more care to it than others, but all of that is something you want to be sure of when you're installing this.
Okay. Well, that's kind of cool. Well, we were trying to keep these to an hour, and it's an
We
hour and a
got going pretty
half.
good.
We did pretty good. This is not too bad. Although we got to work on your video. You're getting a delay on your video.
We'll
Yeah.
we'll get it for the next one.
Yeah. And the next one we're going to have Jim Dollard. And me, you, and him are going to talk about, and possibly David Smith. David is got his second shot for COVID, and the
Wow.
second shot really knocked him down. So um, he's getting back in the saddle again, though, so that's a good thing. And right now he's working on code adoption, so Thursdays are tough for him. But hopefully the next session that we'll do is we will take a look at how these solutions are being recognized by codes and standards. They're not recognized in 24087 and 24067. They're not recognized there, but they are making their way into the 70E safe work practices to recognize the
Hmm.
capabilities. And we're going to
Yep.
explore that in our next session
Yep.
in this regard. Cool.
Awesome.
So, Tamaki, we got Tamaki's. You're welcome. Um, Putting a light on sensor that activates arc quenching device to yes, that makes sense. Yep. So Tamaki, hopefully we answered yours. No fuses to replace. David Engelhart, hey, you're better late than never, buddy. He may be late, but he's worth the wait. Yes. So I think we got all the questions that came in there. I know I got the questions. We answered the questions that came in on email. I wanted to make sure everybody knows that on next Tuesday we're going to be talking getting remote, and we have a special guest, which will be Russ Seyfried, and we are going to be talking about methods to get outside of the arc flash boundary, the challenges there, the risks involved. All of the different aspects of different types of technology. But on Monday, we're going to be talking ground fault circuit interrupters, and I believe we will be talking with Nihad El Sharif. He's going to be dialing in, Matt, from
Oh,
Egypt.
sweet.
This will be our
Oh,
first true international call. And
awesome.
and here's the thing, Matt. When I first went live, I didn't think that I'd have this YouTube channel and everything, right? When I first had an international presence, which will be Nihad, I'm thinking that Felix is on my radar. Okay,
Uh,
I've got a bullseye on Felix Sandoval because I'm thinking South America, I'm thinking Colombia. How do they do business down there? And I'd love to think about other areas of the globe to
mhm.
talk about construction in different parts of the world, different
Yep.
voltages, different frequencies, different
Hmm.
issues, right? I mean, uh,
Yeah.
that would be awesome. So I'm going to be talking to Felix and others out there from an international perspective. I might reach out to our friends in our company that are over in
Yep.
England, right?
Yeah.
And see if we can't talk a little bit about an international place. So maybe some international
Sweet.
standards.
That'd be great.
That'd be awesome. Okay, brother. Well, we've been going for an hour and 34 minutes, and we were supposed to go for an hour, but I enjoyed the discussion so far, and we will pick this one up
Likewise.
again with Jimmy.
Really appreciate it, Tom. It was a really good session. A
I
good,
thank
good
you.
topic for safety month.
Absolutely. It's Electrical Safety Month. Can't forget that. And I love, everybody that it's attending. I appreciate the chats. I appreciate the feedback. Please give us feedback. I'm positive or negative. I mean, if you don't like something, let us know. And if you want to see something talked about, an issue or something, we'll bring that down and get that on the table. But thank you, Matthew, for
Thank
joining
you,
us.
Tom.
I
Enjoyed it.
I appreciate you taking your play time. This should be Miller time, right? So I appreciate you taking time out of your day.
It's all good.
And thanks for
All
what you do
good.
for the industry.
Anytime.
All right,
No
brother.
problem.
Okay, we're everybody out there. Thank you for joining in. Thanks for signing in. Thanks for communicating, and thanks for what you do for the electrical industry, electrical safety, all that jazz. Stay safe, please, and please stay healthy. So we're going to sign off. And Mr. David Engelhart, thank you, Felix, and Boy, and everybody else out there. Tamaki, I don't know. That's all I know is NHZXBOI, and BOI is Boy in my book. So anyway, all right, Tamaki, thank you very much for joining in. So hey, everybody, have a great. Today is Thursday, so have a great weekend. I'm not going to be live tomorrow, but we will see everybody on Monday. 5 o'clock. So we're starting Monday with Nihad El Sharif. Don't forget, that's going to be new. Be here on Monday. Thanks, Matt.
All right.
All righty. Well, that was a good program. I enjoyed that.
Yeah, likewise.